Hey, could you hand me a digital balance? I need to measure out some mass. Digital balance? Like this pan is equal to that pan, or is it more like a digital scale? Well, here we have a balance and a scale together. They both give us about 200 grams. Here we are 200 grams, and we're even there, and then we have about 200 grams on the digital balance, digital scale. Well, let's put them in an elevator. I'm in an elevator, dum-dum-dum, pressing the button. Kind of awkward. Hope no one else needs the elevator here, and things are weird. Things are happening. This is strange. All right, what's happening here? That was a crazy trip. Let's look at it again. Let's focus on two things. Number one, nothing's happening up there, and number two, things are going crazy on our digital balance, our so-called digital balance. As we look at the elevator trip again, things are normal and things are going crazy. So what is happening here? Is it a digital balance? What are we talking about? We're talking about 200 grams. That's our mass. And then as the elevator is accelerating up, that reading goes to 213. And then the elevator stabilizes. We're going up at a constant speed, and the scale reading or the balance reading stabilizes to about 200 grams again. And then as the elevator reaches the top floor, it's slowing down. It's slowing down, so it's accelerating downwards. The scale reading goes down to 187 grams. Again, what's happening here? Let's take a look at it with a spring scale. Originally, we're at rest, an upward spring force, a downward force of gravity. Everything's happy, everything's good, and then we're accelerating upwards. Well, how can you accelerate upwards? F equals ma. Net force is up. The scale reading is bigger, and we are accelerating upwards, and then we're traveling upwards at constant speed. This is surprising to some people that you can travel upwards at constant speed with no net force, but there it is. Acceleration is zero. Force is balanced. We're happy. And then as we reach the top, we are slowing down. We are slowing down, so the net force is down. We are accelerating down. The scale reading is less than 200. So there you go. In short, and it's going to get longer, but in short, you are more like a spring scale, Mr. Electronic Balance thing. You are more like a spring scale, less like a true balance. But let's consider temperature. What about temperature? Here's a thermometer. And a thermometer measures temperature, correct? Well, when you use a thermometer to measure temperature, what are you really doing? You're looking at a length. You're looking at a length, and you're just trusting that the change in temperature of the liquid inside the thermometer will change the length of the column in the tube. See what I'm telling you, you're really trying to look at a difference in length. How long is that blue tube? Or when you look at a graduated cylinder, what are you doing? You're really kind of looking at a length here, aren't you? Aren't you really kind of looking at a length? How high up the graduated cylinder does that liquid go? So in both cases, you're making a decision. A measurement isn't a measurement, a decision. You're making a decision about a length. Well, how does a digital whatever it is work anyway? It works with one of these things. It is a strain gauge, and a strain gauge, not surprisingly, has lots of wires in it. And here's the deal with the wires. When you put this wire inside the digital scale and then the pan moves a little bit, the wire gets deformed. And when the wire gets deformed, it changes the resistance of the wire. Here's an equation for resistance. And when the wire is bent, then its length changes a little bit, and as a result, its area changes a little bit, and the resistance changes, and you can measure that with a digital voltmeter. And that's not something I want to talk about how that works, a digital voltmeter. So is it a digital balance? Well, I would call it a digital scale. Well, not really a digital. How about this? It is a digital voltmeter that can be used to detect changes in the resistance of a wire, which correspond to changes in the length and area of that wire, which correspond to the apparent weight, which is related to mass, unless you're accelerating. Thank you very much to Elaine Rett and Wired Magazine. It was his article in that magazine that inspired this video.